Okay. Okay, so we're going to see if our clickers work. If you haven't registered it, that's okay. We're trying to make sure that our clickers work. And here we're on channel 41. Okay, so let's see. How are we feeling about Chem 131? Super excited? Cautiously optimistic? Anxious? Okay, that's me. I'm anxious about it. Or whatever. I like this choice. Whatever, I don't care. Right? Okay, now there should be approximately 140 of you in here, so we'll try to wait till at least maybe we get to 100. The purpose of us doing this today is to make sure that I can see your clicker responses. Okay, I'll post those grades, quote unquote, on Canvas as the week goes on to make sure that your clicker responses are coming through. Okay? Okay, so let's see what we think. Oh, anxious. Okay, anxious and cautiously optimistic. This is good. This is good. All right? Okay, so let's try our next one here. Why are you taking this class? Just for fun because you're crazy? Okay, that's elective. It's required by your major. You're required by your pre-professional, that's what XX means, or you're a crazy chemistry major. All right, that was me, so that's okay. You're okay if you're a crazy chemistry major. All right, so we got some of those. We did better on this one. Is our batteries working? Fresh batteries, fresh semester, fresh batteries. Okay. All right, so required by your major, so we all have to struggle through together. All right, that's what the majority of us are doing here. Okay, what kind of grade do we want to get? All right, and I use this word here very seriously. That grade earn in there. All right, I'm here to help you guys earn the grade that you want. All right, but you need to help me. Okay? All right, yes. We're all after it, okay? I'll give everyone in this room an A if we earn it. I have no problem with that, okay? So if we're on board, we're cautiously optimistic, we're all heading for A's, it's going to be an awesome semester, okay? All right, and how much work do we think that's going to require? All right, I want to think about how much work it took you in 131, okay? Or how much work you realized at the end it might be taking. All right, look at this. We're willing to put in the work, okay? So we're off to a great start here. All right, this is good stuff. Okay, so now into the boring things we just need to get through. All right, so we do have 4 tests in this class. Unlike other sections, I'm super mean and I do not drop one of those tests. There's a reason for that. The reason is that the final exam doesn't just not care about one section, okay? And whenever you have that feeling that you can drop one test, you tend to have that point in the semester where you relax and you're like, this is going to be my drop test. Just not even going to worry about it, okay? But that material will come back to bite you on the exam. And so I do this to attempt to do you a favor, not to be a jerk, okay? And in the long run, dropping the test doesn't really affect your grade all that much unless you have a complete breakdown and you get a 0, okay? Then a trade Z of grade would happen, okay? I've already had some of you contact me about conflicts with these dates. I appreciate that. If you are in that boat with a serious conflict, please let me know and we can work around that, okay? It's not that if you miss the test, you're going to get a 0 and I'm just not going to exchange that grade, okay? So if you know ahead of time, conferences, travel, sports, anything like that, just please let me know. Okay, your grade in this class is broken up 15% in participation/homework, which involves clicker questions in class. It involves work that we'll do in class. And then it also involves the Learn Smart, which on the syllabus is designated LS, as we look on that massive Canvas syllabus. So that's LS, as well as quizzes that come on Connect, which are designated Q. Okay. I know that there is, you may have come from using Connect and Learn Smart. You may have come from using MindTap. You may have come from using Alex. Okay. And I apologize for some of that confusion. We're in the process of sort of changing the way we do general chemistry. So hopefully all of your questions were answered with my email. Again, if you're having problems, I think I have 75 people registered for Connect, which is not so bad at the moment. Okay, you can register for that 2-week courtesy access, which will give you access to the ebook without buying a hardcover book. If you just want to buy the 1 semester Connect access, you can do that as well. The full year Connect will give you 2 semesters worth, but everybody in here is going to get an A, so we're not even worried about the possibility that you might need another semester. Okay, right? Okay. Then you have 55% from those tests that we'll take in class, and lastly, that final exam, which is 30%. And again, that comes from both 131 and 132 material. All right. The other thing to know about this class is that you can get as much help as you want. Okay, and there's plenty of resources out there. We will have study sessions, weekly study sessions, and I'm going to send out a quiz/survey today that tries to get a feel for what time might work the best for all of you as a group. That's why we don't have a time yet. There are also tutoring sessions. If you took advantage of those free sessions for 131 up on the 3rd floor of chemistry, they're from like 5 p.m. till, I don't know, 8 p.m. every day. All right, so those people are there to help you. That is free. There is a Science and Math Learning Center that is also free. And we do have a past leader in this class, this lovely gentleman over here, Jeremy, if you want to stand up and say hello.
Hello. Okay, so my name's Jeremy. This is my 3rd semester of doing 132 pass. It's my first time with Dr. Boardman. What else? So our sessions right now are looking to be Mondays and Thursday nights around 7. My schedule is pretty packed, so I only have a couple days that work for me. But there's also the SMLC, which has great tutors. You'll be doing your sessions, plus the free tutoring in PhysChem. So there's a lot of options to get help. You guys, if you can't make sessions, for whatever reason, practices, whatever, you can always email me, depending on what time it is, or like how close to tests or finals it is, depends on how much I really will feel about helping you. Because I also have things to do. But if you really can't make it, whatever, and we do like a worksheet or something that I can send you the doc and whatever. Don't ask me for help on quizzes. Don't ask me for help on things that are graded. I can't help you on those. But the sessions will be good and a lot of fun, and it will start on Monday.
This coming Monday, like next Monday.
Yes. I still have to wait for the time, but it will be on Monday. And I also, so since the final is half, 131, 132, we always go through some 131 stuff. And 132 stuff. But yeah, that's pretty much it. And also there's a study guide I just sent to you. So I have a study guide. It's basically my notes when I took the class. It's like 4 pages. It covers everything we are going to cover in this class. So be on Canvas. Feel free to use that as much as you want. And maybe if I send you the worksheets, whatever, you get those on Canvas too. So then if you can't make it and want extra problems, those will be there too. And then we'll do test review sessions. Those are usually 2 hours long. The way I like to do those, though, is send out a practice test that's roughly 22 questions, just like a regular test. I find it kind of a waste of time to do it during the pass session because in the last few times I've done this, we've taken the full 2 hours to go over all those questions and the other questions. So I like to have people do it beforehand, or at least look over it beforehand. But the sessions go a lot better if you come with questions. I will come with a structure of things you can do, but I'd love to just do, I'd love to change that if you guys have topics you'd rather cover or whatever. So and it kind of depends on who shows up and how that goes. So but I'm looking forward to it. So I'm going to pass. It's really good. Thank you.
Thanks, Jeremy. And I do see Jeremy frequently. He is a chemistry major. He has suffered through classes with me and survived. So we will be in communication about stuff that's working in class or not working in class. So know that we're both here to help you guys as much as possible. Okay, so this won't work. That's okay. Oh man, okay. The computer and I last semester had a little bit of an argument sometimes. So what you'll see actually here in the corner on every slide that I give lecture on reminds you when my actual office hours are. They are Monday and Wednesday from 1 to 3, and then Tuesday, Thursday from 10 to 11. If those hours do not work for you, just feel free to send me an email. I'm almost always in my office, which is right across from my research laboratory. If you just happen to stop by, if my door is open, I am there and willing to help you. Okay? If you're nervous to come see me by yourself, bring a friend. I promise I'm not that scary in real life, and it's really useful to come to office hours. Okay? So take advantage of those as soon as you can. Right? You don't want to come and see me when you're completely lost in the middle of the semester. Right? It's better to stay with it. So this semester, what we're going to do, okay, is we're going to cover not quite as many topics as you did in 131. The first thing we're going to be focused on is how and why solutions form. All right, and this is going to pick up on some of the skills that you guys used in 131. All right, but now we're all big people scientists. All right, and we need to apply that knowledge we've learned in 131. Okay, we're then going to focus on reactions. All right, and reactions were always everybody's, I feel like, nightmare in 131. Right, we write two reactants down and we're trying to figure out what products are formed. Okay, but this semester we're going to decide whether or not that reaction will occur. Right, we're going to decide how we know when that reaction is quote unquote done. All right, does it go to completion? Does it reach some type of equilibrium? And how do we know how much material is left at that point? And then lastly, how fast do these reactions occur? Okay. I don't really see a whole lot of chemistry words here. Right? Solutions is maybe a chemistry word, but I'm confident that we know that word. All right? But you want to think about these different topics that we're going to learn into one of these categories. Will the reaction go? How do we know when it's done? And how fast can we get there? Okay? These are going to be the topics that we're going to cover this semester. Okay? And I like to start this way. And this is in part because my dad was my high school chemistry teacher. All right, and he was crazy. You'll hear me tell all sorts of stories about him as we go through, and that's because the man was crazy, and I still remember exactly when he uses really weird examples. So I apologize if some of the examples will seem odd. Okay, but he always started every class this way, and this is a Shel Silverstein poem, okay, called Melinda May. Have you heard of tiny Melinda May, who ate a monstrous whale? She thought she could, she said she would, so she started right at the tail. And everyone said, you're much too small, but that didn't bother Melinda at all. She took little bites, she chewed very slow, just like a good girl should. And 89 years later, she ate the whole whale because she said she would. Okay. Now I'd like to say we don't have 89 years to finish all of these chemistry topics. Okay. We only have now a full year, one semester to finish that. And we are going to take little bites of this monstrous whale known as chemistry, and we are all going to finish it. All right, because I have confidence in you. So I always like to start that way because it reminds me of my dad, and it's always a good way to think about it, right? You don't want to view this course as something so massive that you have no hope of finishing. All right? You want to think of it as baby steps that are going to get us through, and at the end you look back and you're like, holy shit, I just ate a whale. Okay? That's what I want you to feel at the end of the semester. Okay? And because you want to feel proud of doing that. Okay. So that being said, what we're going to do today, it looked like most people found their way to the Canvas site. Okay? I assume if you had Dr. Warner in the fall, that Canvas site should look very similar. And I'm doing that to follow in Dr. Warner's footsteps. So hopefully that's all making sense. The things I want you to be aware of on there, okay, is every day I'll try to start this way with what's due in the upcoming classes. But if you want to look back at that, all right, that is all here on Canvas. All right, this is our syllabus schedule, the policies, if you want to see that good stuff. But this is basically how every day is going to go, right? We have what's due before class, the slides that we're going to cover in class, and then after class I will put the link to the lecture recording there. If there are any other recordings that are helpful, they're also posted in this column. If you check out these two videos, they are from Dr. Warner, so it will be Dr. Warner's voice over that video. And you can also see, like, for example, here on Wednesday, Learn Smart 12.3, 13.1, and 3 and 4 are due. Okay. They will not close until Friday because, again, we're sort of all figuring out how to use the system. Okay, so I don't need 1,000 panicked emails this week that's like, Connect won't work. I can't get the Learn Smart done. Okay? If that happens, and Connect is doing something really strange, you want to use their support, okay? Because computers are my nightmare. So you really want to go to that Connect support if you need it. Again, feel free to use that 2-week courtesy access. That's going to give you 2 weeks free while you figure out what's all going on. And you can also see there if you like the ebook, if you didn't purchase a hardcover book, which the hardcover book looks like this, okay? There is a special edition for JMU. If you find a cheaper 7th edition somewhere else, go for it, okay? The one for JMU, there's not anything super special. We've just taken out some of the chapters that we don't use. Okay. So again, all the things that are due should be here. I will update this as we go throughout the semester. Okay, but so today, okay, you want to make sure that you get that Connect going, and this clicker registration I'll see when I get back to my office and download that to see how your clicker registration is going. Again, there's a link to that in the Canvas page. So for Wednesday, we're going to start with a clicker quiz at the beginning of the class, just on some simple syllabus things. You know, how many tests do we have? Not anything crazy. I just want to make sure you go through and read some of those policies, just so that we're all on the same page. Okay? It's not a 30-page, you know, I agree to the terms and conditions of this nightmare. Okay? It's not like that. Again, it's another way to make sure our clickers are working. And so today what I hope to get us through is a refresher of sort of how 131 ended, okay, with respect to intermolecular forces. So can we identify different intermolecular forces, and can we rank them? The other thing you'll note on here is there are specific learning objectives. There is a sheet that has all of the in-class problems and the learning objectives for each chapter on Canvas. Let me just show you where that is real quick. Okay, so up here in the 132 objectives and practice assignments, okay, this is a full PDF of all of the information that we're going to cover, and it looks super overwhelming. Okay, all of these problems are for practice, okay, to be done before you take that online Connect quiz. All right, the solutions to these problems are also on the Canvas syllabus page. Okay, so all of the in-book solutions are there, but these are all of the questions you'd like to have done before you try to do that Connect quiz. And the way those Connect quizzes will work is if you get an 80% or better on that quiz, it counts as a complete. Okay, so at the end of the semester, let's say there's 15, which I think there's definitely more than that. Okay, but if you've got an 80 or better on all 15, you get 100%. All right, if you have 2 that are less than that, okay, that changes your grade. But really try to get that 100% on your Connect. It drastically improves your grade. And it's basically free points, right? You have the practice problems, you have the solutions. You can really, really bolster your grade if you get those Connect problems done. Okay. And this is where these, so let's say learning objective 13A and B, that's where they come here. Okay, so if you think there's some random numbers, that's totally fine. You don't have to go back and look at them. It's just so that you can see what our plan is on learning something every day. Okay, so if we're talking about solutions and intermolecular forces, we're looking to answer questions like, will these mix? Okay, will they make a solution? Okay, so do sugar and water mix? Have you ever made Kool-Aid? How about oil and water? No. Okay? This is one of my more, I also really like to tell really terrible nerd jokes, so I apologize in advance for that. Okay? But this goes along with, why did the white bear dissolve in water? Because he's polar. See, you laugh, but you missed it. Okay, I don't care if you make this mistake. You can laugh at me or at the joke, but that's why, right? It's polar. Okay, so like things dissolve like, but those like interactions have to do with intermolecular forces. All right. We also want to think about how temperature and pressure affect solubility. Okay. So What happens to a solution when you heat it up? Does more or less of the solute go in? Okay? What happens when I put pressure on a solution? Does more or less solute go in? Okay, and this is going to be different when we're thinking about solids, liquids, or gases going into solution. All right, so we need to think about intermolecular forces. We need to think about temperature and pressure. And we also are going to investigate how these solution properties are different from the pure solvent. Okay, so for example, pure water versus salt water. Okay, what type of interactions are in those two, the pure solvent versus the solution? Okay, and what type of properties do they have? Melting point, boiling point. Okay, how are those properties affected from going from the pure solution of just water to, say, having salt in it? Okay, so the things that you need to remember from 131 to be able to do these, okay, are molarity. Who can tell me what the units of molarity are? Not Jeremy. Moles over liters, okay? Moles per liter. That's a value of concentration, right? So if I'm concerned about what a solute does into a solvent, I need to know how much stuff I put in there, right? So that's molarity. I also have delta H, or enthalpy, all right? That has to do with the amount of heat, okay, that's either required to do the dissolving or the heat that comes off, right? What's the value of delta H for an exothermic reaction? Here's some mumblings. Our choices are negative or positive? Negative. Negative, right? Exo, negative. How about endothermic then? Positive. Positive. See, look at this. We're dusting those cobwebs off from 131. All right, we're all doing a great job. We also have Hess's law in there. Okay? Hess's law is one of my favorites because I get to cross stuff out. All right, if I take multiple steps and I can get to an overall step that has an overall delta H to it. All right, and then again, these intermolecular forces. So if I'm thinking about intermolecular forces, they can explain physical properties, like I said, of boiling point and melting point and vapor pressure. Okay. So if I think about, let's say, sodium chloride as an example. Okay. Does sodium chloride boil at room temperature? Now you're looking like you're crazy, right? Because sodium chloride is a solid, right? So at room temperature, I shake it on my food. Okay. I also throw it, well, we throw something else, not really sodium chloride, on the streets out here when it's cold. Okay? But what does it help to do on the roads? Okay, it messes with the freezing point. Okay? And that's actually a really key difference, because people say the ice melts the water. Okay, that makes no sense. It don't melt the water, okay? But what it does is it actually changes the freezing point of the water or the precipitation that falls on the ground, all due to intermolecular forces. Okay? So that's how we're affecting the melting point. And boiling point, do we know what's true about the vapor pressure and the atmospheric pressure when something boils? I'm trying to remember if we actually learned about this in 131. Okay, do we remember what the vapor pressure is? You get a lot of like, oh no. Okay. Does water have a smell? No. How about ethanol or acetone, things you use in lab?
Yes.
Does that stuff smell? Okay. That's because the molecules are being put up into the vapor phase and you smell them. Okay? And you can affect that vapor pressure because of intermolecular forces. Okay, water has very strong intermolecular forces. Something like ether, ethanol has lower intermolecular forces, so those molecules can get up into the vapor phase much more easily. But when the vapor pressure and the atmospheric pressure are the same, the liquid will boil. Okay? So if I can affect how easily something gets up into the vapor phase, via intermolecular forces, I can affect the boiling point. Okay, and when I'm thinking about these different components in solution, all right, I can have ions. So here I'm depicting a cation. Okay, what's the negative partner to a cation called? An anion. All right, nicely done. So I can have charged ions. All right, it can also have nonpolar molecules. Let's take hydrogen gas, for example. Okay, hydrogen gas is a nonpolar molecule. Even O2 gas, right? Any diatomic gas will be that way. We could have something like this, like ammonia, something that has a nitrogen with 3 hydrogens attached, and that molecule is going to be polar. Right? So when a molecule is polar, you have this unequal distribution of charge because you have somebody that's more electronegative. Right? So he wants that charge more than the other person, and it imparts a dipole, or you get a polar molecule. So water, for example, that's what this guy over here is showing. Right? Oxygen is electronegative, where hydrogens are electropositive. Okay, so let's look at the overall craziness back from intermolecular forces. All right, this was probably a table you saw in 131 or something like this, and this goes from the strongest down to the weakest force. Okay, so the strongest one you actually can have is ion-ion. Okay, ion-ion is why sodium chloride is an ionic salt. Okay, so ion-ion becomes an ionic bond. All right, so technically you don't often think of that as an intermolecular force because it forms a bond. But you can have ion dipole, right? So a cation or an anion with a polar molecule. Here I'm showing sodium cation with water. I then have hydrogen bonding, which is a special case of dipole-dipole. Okay, so in hydrogen bonding, you have a hydrogen bond that has a dipole, and it's then found in either nitrogen, oxygen, or fluorine. Okay, so water forms hydrogen bonds. Any alcohol can form hydrogen bonds. All right, but you want to be careful about whether it's in the pure solvent or mixing with something else. You then have dipole-dipole. Okay, I have ion-induced dipole, dipole-induced dipole, and dispersion forces. Okay, so if you are a completely nonpolar molecule, you only have dispersion forces as your choice. That being said, even polar molecules, okay, technically every single molecule there is has dispersion forces. So oftentimes on a homework, it'll ask you for the intermolecular forces between things, and you select, let's say, dipole-dipole, and it marks it wrong. You're like, okay. It's usually because it also wants you to check dispersion forces. All right? And that is because dispersion is in every single molecule. It's just the weakest of all of them. Okay, so let's look at these guys. Again, I've listed them as from strongest in ion dipole over to dispersion. Okay, so let's see if I can actually write on here. Okay, so we know that, maybe, oh no, it's not going to work. That's dangerous. Okay, so we know everybody has dispersion, but I want to look and say, okay, let me search for the ion dipole. And if you have this printed out, what I would do is I would draw a line, which I was planning to do with that pen, but me and the computer aren't friends yet, to say ion dipole comes over to this guy. All right, so I have a sodium cation, and these are water molecules surrounding that sodium cation. Do I put the positive or negative end of water towards the sodium? I hear one vote for negative. Are we on board with negative, or are we not on board with negative? Okay. Because, right, opposites attract. I don't want to put the positively charged hydrogens towards the sodium because then they would just bounce off one another. Okay. So I have the negative oxygen dipole pointed towards my sodium. Okay. Then I want to look at hydrogen bonding. Okay, and that belongs to this set right down here. right, so I have methanol, and that is hydrogen bonding, right? This hydrogen that's on the oxygen to the oxygen of the water. Okay. Methanol and water can hydrogen bond with themselves, okay? But in this case, I'm showing the mixture of methanol and water together. All right, so now I'm on to dipole-dipole. Okay, dipole-dipole exists right over here. Here's methanol, and here's chloroform. Okay, chloroform has the structure CHCl3, okay, but it cannot hydrogen bond. Okay, because the hydrogen on chloroform is not bound to a nitrogen, oxygen, or fluorine. Okay, so we want to look at the difference between why this methanol and water can hydrogen bond, but the methanol and chloroform cannot. Okay. How about, again, can methanol hydrogen bond itself? Yes, yes. Can chloroform hydrogen bond itself? Okay, so if the answer to can I hydrogen bond myself is not yes, okay, in both cases, then you get just a dipole-dipole, not a hydrogen bond. All right, so you want to ask yourself that question about each component. Can I hydrogen bond? If the answer to each component is yes, then they can hydrogen bond with one another. If one of them is no, only dipole-dipole is the case. All right. Okay, so then I'm looking at ion-induced dipole. Okay. I need an ion. Okay, that should be obvious. But if I'm inducing a dipole, does that mean that my molecule is polar or nonpolar? Who votes for polar? Who votes for nonpolar? Yes. Okay, nonpolar. Right? Because if I'm polar, I already have a dipole. Right? So if I need to have a dipole induced, that means that I was nonpolar. All right? So here, this chloride comes up to the hexanes, and the hexanes electrons run away. All right? Because, right, if I'm putting a lot of negative charge in here, my electrons are trying to get the heck away from there, right? Because same Z's repel. Right, so here comes the chlorine to the hexanes, okay, to the table. All of these electrons on this end are like, get me the heck out of here! Okay, and they all run over here. And when they're all running over here, that leaves that end partially positive. So then I have that attraction from the ion to the induced dipole. Okay. This is the strongest of the induced dipole type interactions. Dipole-induced dipole, actually I do not have pictured on the slide. Okay? But I could take hexanes as my nonpolar component, and then I could put methanol or water or chloroform with them. And that would be a dipole-induced dipole interaction. Right? So if you put something polar with something nonpolar, you have your dipole-induced dipole interaction. And then lastly, for dispersion, right, the trick question, they all have dispersion. But this octane and hexane, these two guys together only have dispersion. Okay. So if you are a nonpolar molecule and you are mixed with a nonpolar molecule, your only option is dispersion. You do, again, want to remember that there is a pecking order here. Okay? And when we think about making solutions, these are the types of forces we're going to be thinking about. Okay. So, we want to now jump into a little bit of this solution-making process. There's a figure that's going to come from your text, figure 13.14. And we want to think about what's happening when we actually dissolve something in water. Okay, I lied. This is hexane. So I'm going to take salt, sodium chloride, and I'm going to put it in hexane. And there's a couple of things that have to happen in order to do this solution process. Okay. The first thing is here I have hexanes, okay, and it's in what they call the aggregate state, where it's all the atoms, or molecules I should say, are close to one another. What type of intermolecular forces, all right, does hexanes have just by itself?
Dispersion.
You got to vote for dispersion. We okay with dispersion only? Okay, hexanes, right, is a carbon-hydrogen chain. All right, does that make him polar or non-polar?
Non-polar.
Good. You get some votes for non-polar. Okay. All right, so if hexanes is non-polar, his only option is dispersion forces. Right? That's the only option. So do we think it's hard or easy to just sort of shake them up a little bit? Well, maybe I should ask this. Are dispersion forces the strongest or the weakest?
Weakest.
The weakest. Okay? So if they're the weakest forces, should they be easy to break? Okay? The weaker the force, the easier it is to break up. Okay? So this process here, this delta H is going to be reasonably small. Okay? Because it's not that difficult to break these guys up. Okay? Now if I think about sodium chloride as a solid, okay, so to break sodium chloride up into its charged species by themselves, do we think that's hard or easy? Okay, I got votes for hard. Why? Because it's ionic, right? Those positive and minuses, they want to be right next to each other. Okay, they don't want you to break them up. Okay, they don't like that. So actually taking something from this solid state, okay, into this separated scenario is going to be very challenging. Okay. But what about what happens here when I actually make the solution? Okay, now I have hexane and I have sodium and chloride ions in here. Okay, so out of 1 through 6, okay, which number am I now having an intermolecular forces here in the solution? Okay, do I have any takers for number 1? No. Okay, good. Okay, how about hydrogen bonding? No? Right? The answer is no to hydrogen bonding in each of those cases. Right? Hexanes cannot hydrogen bond. Sodium chloride cannot hydrogen bond. No hydrogen bond. Okay. How about a dipole-dipole? Nope, I'm seeing some of these. Okay. How about an ion-induced dipole? Ooh, I see one. Yes. 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 Right? I see an ion. Ding. Okay. I have an ion, and then I have this non-polar hexanes. Okay, which can only have induced dipole or dispersion forces. So number 4, all right, is what I got going on in here, as well as number 6. Right? Because I can't forget that everybody has dispersion forces. But you want to be, thoughtful about the ones that you pick. Okay? If there's an ion in there, it can only be 1 or 4. Right? Don't go crazy on that test circle in something that doesn't make any sense. Okay? Because you know they're out there to get you. Right? If there's an ion, look for that one that says ion. And then say to yourself, okay, what does my other component have? Is it a dipole or is it not? Okay. So I like to think about the intermolecular forces by thinking about one piece at a time. and asking myself what intermolecular forces are even possible for that component. So when we put this all together, okay, we can see what's going on here, that I start with my hexanes all together. I have to separate that guy, okay? That takes some amount of energy, but it's pretty small, right? Because again, those dispersion forces are pretty weak, okay? Then what I have to do, right, is take my sodium chloride aggregated and put it into sodium cations in the gas phase and chloride anions in the gas phase. That takes a whole heck of a lot of energy to do. Okay, and that's why they have this little break going on. Okay, because this is not to scale. The amount of energy required to do this to sodium chloride is insanely larger than that of hexanes. Okay. But you then have, you get a little bit of that heat back when you mix, and so overall you have a solution process that requires a certain amount of energy to proceed. Okay. And you know, solubilities are different than others, right? Sodium chloride dissolves pretty easily in water. Okay, it dissolves even better in warm water. Okay, and that's true because if you have warm water, you're putting this energy in and making this change much easier. Okay. Yeah.
So it takes energy to break one, right? So that's endothermic, but then to form one, it's exothermic. So is that what the downward arrow is?
Absolutely. Okay. So you regain some of that back, that energy back, because you're making favorable intermolecular reactions. So yeah, that would be exothermic. Okay. And you see that in lab, right? Exo and endothermic is a really sometimes hard concept to wrap your brain around a little bit. Right? So when you mix two things together and you feel the beaker, you know, whether it feels warm or the beaker feels cold. Right? Those are ways to know. If the beaker feels hot, is energy being given off or being required? Given off. And if energy is being given off, is it exo or endo? Exo. Okay? So that's if I feel that it's warm, okay? If I feel that it's cold, right, it's cold to the touch, that process requires energy from the outside to happen, and that's endo. Okay? And they make really, you know, the sweet both ice packs and heat, you know, now we're in hot hands time of year. Okay? You mix that up, that stays hot for like 0.2 seconds in this cold, right? But that's an exothermic reaction. The same is true with those old-fashioned elementary school ice packs. Right? You get hurt in gym, they crack that thing, they shake it up, and it's cold. Right? That's an endothermic reaction. So knowing, hey, this is again, whether a reaction will happen, these are all sorts of things we're going to learn this semester, and why that's the case. Okay? But to get another little sort of hint on that, okay, let's think about sodium chloride dissolving in water. Okay? This is a highlighter. That is not a right on the board marker. Okay, so here I have sodium chloride, and I'm starting with sodium chloride solid. All right. So that involves breaking the lattice. Okay, the lattice is that cations and anions perfectly arranged together to make our solid crystal structure. Okay, and in order to do that, I have to go from sodium chloride solid to sodium plus gas and Cl minus gas. Okay, again, is this going to be a positive delta H or a negative delta H? Do we think it takes energy to do that transformation? Yes, okay? So if I have to turn the burner on to make it go, am I putting energy in? And that makes it positive and endothermic. Nailed it. Okay? So that's an endothermic transformation. That requires a whole lot of energy. Okay? And what's happening here, that's to break the lattice, okay? And that's why this jump here is so large. Okay, so this is energy or enthalpy here on the left axis. or on the vertical axis, I should say. So that gives everybody into the gas phase, right? Then I have to go for the hydration, or this delta H of hydration, which involves the breaking up water, okay, in that aggregate form, and also the delta H of mixing, which has to do with what happens energetically when you put the ion with the water. Okay? Do the ion and the water like each other? Sure. Okay, because my ion is charged, right? I have both cations and anions, and I have polar water. All right, so there's going to be a favorable ion-dipole interaction there when I take my sodium plus in the gas phase to sodium plus aqueous. Okay. I also have to do, right, Cl minus in the gas phase going to Cl minus in the aqueous phase. All right, so that involves that delta H of hydration. Okay, and you can see that that overall is going to be an exothermic process. Okay, our energy is given off because I've now separated the ions and they're super cranky because they're in this high energy state, and now I've put them back with water. Okay, so they're kind of happy because they have a counterpoint to their charge. So overall, okay, what I'm doing is I'm taking sodium chloride solid to sodium plus aqueous plus Cl minus aqueous. Okay. And that uses Hess's law to cross out. Okay, I really wish that I could make myself right on the screen here because that would be easier. But when I push this dude, still, no, okay. So I can cross out, right? Hess's law would allow me to cross out sodium gas here with sodium cation gas on this side. All right, and the same with Cl minus. Cl minus gas crosses out here, and it would cross out on this side, which I wrote on the board. Okay, so overall, I get sodium chloride solid goes to sodium plus aqueous, Cl minus aqueous. Okay, and I'm going to get, right, this final delta H with respect to that transformation. Okay, and that's why that change is usually slightly endothermic. Okay, it depends a little bit on the salt and the compounds that are being used, but the reason it's slightly endothermic is because of this initial having to break apart the lattice. Okay, but you want to take home message for today is that the solution process requires both a breaking of the lattice, but also this delta H of hydration. Okay. All right, so we will end there today. We'll see you all on Wednesday. Please try to make sure you get your Connect going, and if you have any problems, let me know.